the end of the month?
At the end of this month. On the first?
Sorry?
At the first time.
No, maybe not. Okay, so last class, by studying the symmetric exclusion process, we are trying to prove that at any time t, if I consider the empirical measure at a time which is accelerated by n squared, then this object converges to a measure which is absolutely continuous with respect to the Lebesgue measure and whose density satisfies some PD, right? So what we did is that we introduced a test function, which we took in C2, and we proved two things, that we have a martingale, which is pi nt integrated with respect to g minus, and here we computed, okay, so let me write it, L it's the generator, so this we computed, and it is and we have, due to the Laplacian, the discrete Laplacian, a factor 1 over n squared. And then, okay, so let me change this martingale just to make it equal to 0 at time 0. So I will subtract to this martingale pi n at time 0 g. Okay, so this is a constant. So if this is a martingale minus this constant, it's still a martingale. But now this new martingale is 0 at time 0. And then I claimed that if I take this square and minus something I call gamma n, that this is a martingale where gamma n of S is L by, where is minus 2. So we show that gamma is given by that, and that this martingale square minus this gamma, it's a martingale. Okay? And what I claim is that, well, if you subtract this constant, the same computation show that this is still a martingale. Okay? And we computed gamma ns, and gamma ns was the sum of the gradient of g square times eta x plus e minus eta x square, and I had here a factor 1 over n to the 4. Yes?
Square in the first generator, right?
Yeah. L, this object square, minus 2 pi L pi. Fine. So this is what the computation we did last time, and now I want to use that in order to prove the hydrodynamical limit. Okay, so my first observation is that we have this n 1 over n squared. So instead of looking this process at time t, I will observe it at time, as we said, tn squared. So let me accelerate this time by tn squared, and the only thing that will change is this tn squared. Right? Now, let me here make a change of variables. S prime, it's equal to n s divided by n squared. So if I do this modification, this martingale at time n squared. So maybe let me call that m and gt. So it's still a martingale, and this is simply pi n tn squared g. And now if I do, well, I still have at time 0. If I do this modification, you see that when s is equal to tn squared, s prime will be t. So the integral will be from 0 to t. And here I get ds divided by n squared, it's ds prime. So this n squared will disappear. And then minus, as I said, here it will be t. Here the n squared will be ds prime, but here s, it's s prime n squared. So what we get is that this is pi n s n squared g ds. And now everything is order 1. Okay? So this is order 1, this is order 1, and this is order 1. Then I will use something which is called Doob inequality about martingale. So Doob inequality tells me that the probability that the supremum for t less than t of, if I have a martingale mt square, that this is less than a, this is bounded by 1 over a expectation of mt square. Okay, actually we can so this is very similar to an inequality that you know, in which I have a sum of IID random variables. Okay? If you remember, in the course in probability, if I have xj, a sequence of IID random variable of mean 0 and with second expectation, then I can estimate the probability that max less than a, it's bounded by a. Okay? And the same proof, if you recall that result, the same proof will give you this inequality. So if you remember, the proof of this inequality was just saying, well, let's consider the first time at which this happens. And then you divide your space according to the time at which this happens, and you get that inequality. Okay, so well, if you want me, after the lecture, I can show you the proof of this inequality.
You don't need the expectation of already a description.
Yeah, so MT it's a martingale. So the expectation it's constant. and it's 0 at 0. Okay, so you know the expectation, it's constant and it's equal to 0. Fine. So I will use this inequality for this martingale. So I know that by Doob inequality, I know that the probability that the supremum for t less than t of m, how we call that, mgn t square less than epsilon, that this is bounded by 1 over epsilon, the expectation of m g n t square. Okay, so this is what I know. Now, I will use now this fact that this object here, it's a martingale, to estimate the expectation. Okay, since this is a martingale, the expectation, so now let's go to the martingale mg. Mind that mg is the mg at tn square. So here again, I'm looking at this martingale at time tn square, so I have a factor tn square here. Okay? So the expectation, so let's look at this expectation. The expectation of m n g t square, that this is equal to the expectation of m g n at time tn square, and this is a martingale. At time 0, since I took out this term, this martingale is equal to 0. So this martingale is 0, this one it's also 0. So this is a mean 0 martingale, and therefore its expectation, it's constant, equal to 0, which means that the expectation of this expression is equal to that one. So this is equal to the expectation from 0 to tn square of gamma, but gamma we computed is this expression. Okay, and this expression, as I mentioned, this is an order 1 term. This is bounded by 1, this difference. This, it's order 1, because the gradient, discrete gradient, is n times the difference. G, it's smooth, so it's bounded by 1. Here I have n terms, and here I'm dividing it by n over 4. So this is bounded by a constant, which depends on the function g, divided by n cubed. Okay, so gamma n, it's bounded by constant divided by n cubed. So this is bounded by the constant, which depends on g, divided by n cubed. And here I have an integral from 0 to tn square. So this is bounded by tn square. So this is equal to a constant, which depends on g, divided by n times t, which converges to 0 as n tends to infinity. So this means that this probability tends to infinity. So what we proved, conclusion, is that for all g in C2t, the probability that the supremum for t less than t of m g n t larger than epsilon this tends to 0. Fine? Do you agree? So this is what we proved. But this martingale, it's a function of the empirical measure. Okay? So what we have is that the probability that the supremum for t less than t of the integral of pi nt g minus pi n0 g minus the integral from 0 to t pi ns Laplacian g ds, that this is larger than epsilon, this tends to 0. So this is for all epsilon and for all g in C2. So you see that this expression, it's an expression which can be written in terms of the empirical measure. So I have a function of the empirical measure, and now I can recall that this process is defined in some space, and through this empirical measure, I define a measure on the space D0T, and here the space of positive measures with total mass bounded by 1 with the weak topology, which is a metric space. And so this measure here, it's sent, so with this, mind that here I'm speeding up time by n squared. Okay? So by taking this function, which sends this space into this space, I can define a sequence of measures in this space. Okay, so I started from a product measure with a certain density profile. I had a continuous time Markov chain. So this defined me a measure in this space. And now with this function, I send this measure to that measure. And let me call this measure, remember, pi, u, and rho. So this is a measure here. And what we know about this measure, it's exactly what I wrote over there, because I have exactly this object. Right? So I fix a function g, which is C2, and I first observe that I can replace in this expression the discrete Laplacian by the second derivative of g. Because, well, g, it's C2, so I can do a Taylor expansion, and from this Taylor expansion I can show that the difference between the discrete Laplacian and the continuous Laplacian, so the second derivative of this function, since we are in dimension 1, that this is small, uniformly. And since it's small uniformly, well, I can do a triangle argument to say that I can replace this by that. Okay, so actually I can replace the discrete Laplacian by the continuous Laplacian. And now I have a function from D0T m to r, which to a trajectory pi associates, well, let's say the supremum phi tg minus pi 0g minus the integral from 0 to t by s, the second derivative of s ds. And this function, I claim it's continuous. So you take a trajectory pi for each, so it's these are the right continuous with left limit trajectories from 0t to m pi. To a trajectory, I associate this real number, and what I claim is that this is continuous for the Skorohod topology, which I discussed a few weeks ago. Okay, and then you can check, right? You assume that you have a sequence pi n, which converges to pi. What you know from this convergence in the Skorohod topology is that you can change your time through lambda n such that then this converges to pi uniformly. And from that, you can check then that you have this convergence. Okay? So you have to check that this is a continuous function in the Skorohod topology, which is not difficult. And since it is continuous, what you conclude is that assume that pi, this sequence pi n, rho, it's converging weakly to a measure pi, p, then p of this function larger than delta, it's equal to the limit. Or more precisely, we have seen that weak convergence means so a sequence pi n converge to pi weakly. We have seen if and only if for all continuous function, bounded continuous function fb, you have that the integral of f converge to FDP. Right? So this is the definition of weak convergence, but you can prove, so these are convergence of continuous function, but we can translate that into convergence of closed sets or open sets. So this happens if and only if for all closed set f, you have that, so what is p of f? So p of f will be larger or equal than the limit sup of pnf. Okay, so this is if and only if, or if and only if for all open sets G or H or A, PA, it's less or equal than the limit inf, or PNA. Okay, and since this function here it's continuous, the probability that this continuous function takes a value above epsilon, strictly above epsilon, it's an open set. And therefore you know from this that the limiting measure, it's bounded by the limit inf of these measures. And since you know that the limit well, this is what we proved, that the limit it's equal converge to 0. This is what we proved. Then the measure, the limiting measure will be satisfy that inequality. All right? Questions about that? So here I used, well, this Doob inequality, which concerns martingales, and then these properties of quick convergence. Okay. So what I know is that so if this sequence converge, or if a subsequence converge to P, then P is such that this happens for all G in C2 and all epsilons. Okay. So now you have that this probability is equal to 0. So take a family GK of C2 functions. So this is true for any G in C2 and any epsilon. So first send epsilon to 0 to get that the probability that this supremum take epsilon to 0 to get that the probability that it's positive is 0, which means that the probability that is 0 is 1. Okay? Now, consider family GK. Of functions which are C2 and dense in CT. For the L infinity. So since this is true for, you take for any k, then you can take the union of all k. The probability that this is positive will still be equal to 0, so if you take the union, or maybe here I'm taking the intersection, since I'm taking it equal to 0. So I take every event has probability 1, so if you take an intersection of events with probability 1, it still has probability 1. So what you conclude is that P, this measure P, it's concentrated on P, on measures PTDX, on trajectories PTDX, such that this holds with probability 1, which means you know that this supremum, so you know that PT GK, it's equal to P0 GK plus 0t PS GK second ds, and this holds for all t and for all k. Okay? Since it holds for all k, so t in 0t, so since we consider a sequence which is dense in CT, you can pass to the limit and obtain that actually this holds for all G in C2. You take a G in C2, since the sequence is dense, you can approximate it by a function, a sequence, a subsequence in this family. So what you get is that no problems?
What do you mean by the derivative?
Sorry?
What do you mean by g double prime theta?
Well, this is the second derivative of g. So
It will be the subalert derivative?
no, g it's in C2. So you fix a function g in C2, and what you need is to find the sequence which it's countable, and such that for any g in C2 you can approximate this g by a subsequence here, gk, or linear combination, such that these gk's will converge and the second derivative will converge. Okay? Questions? Well, because I can put here only a countable family. Okay, I know that this holds, yeah, you're right. I know that this holds for any g. Any g. I don't need to go to this argument. That's right. So I know that this holds for any g in C2, from which I get that. Okay, I don't need these approximating these functions. Okay? Fine. Now, yes. Exactly.
So in this case, if you replace it, the time is proportional to n squared by n to the power of theta for theta larger than 1, will it still work? The only thing you use is just 1 over.
So you want to replace Tn square by Tn theta. Larger than? Okay. So you have to be careful. If theta is between 0, 1, and 2, then this will disappear. This term will disappear. Okay, because remember you had here, this term was of order 1 over n squared. So I replace t by tn squared, but if you replace t by tn theta, what you'll get is tn theta by n squared, and this will disappear. So for theta between 1 and 2, you'll get that this is 0. So that pt is equal to p0. And this is exactly what we obtained for the independent random walks. Right? We observed that nothing changed if we didn't rescale time by n squared if the jumps were symmetric. So theta equal to 2, you know what it is. For theta larger than 2, then you're in trouble here. So really need to rescale time by n squared. Okay? Fine. So you see, what we are proving is that this pi, it's the solution of the heat equation in the weak sense. Because if I'm integrated by parts here, what I will get is that for all j this is true, which means that pt will be equal to p0 plus the integral from 0 to t of the second derivative of pi. Okay? So this is one claim that we proved, that any limiting point of this sequence Pn, it's such that this holds for all t and all g in C2. Now what I want to say is that this measure pi t dx, that it is absolutely continuous with respect to the Lebesgue measure. So that actually this measure has a density which I will represent by rho. And this comes from the fact that there is at most one particle per site. So I know that the probability that the supremum between t and t of pi n t any function h, so take a function h, let's say in Ct, that this is bounded by 1 over n, the sum in x of hx plus epsilon, if you wish. Oh, I don't need plus epsilon. This is bounded by that. Why is this inequality true? Because this object here, by definition of pi nt, this is 1 over n, the sum of x, hx, eta tx. Right? And since eta t is bounded by 1, I have this inequality with probability 1. Okay? So again, I can say that this is bounded plus epsilon, and now I have an open set. So now, okay, no, sorry, this is closed, so it's fine. Since it's a closed set and this probability is 1, what I get is I can pass to the limit and get the same thing for any limiting measure. And here, this is converging to the L1 . Okay, this set, it's a closed set, so I can use that the measure of a closed set is larger than the limit sup, but the limit sup it's 1, so this probability is 1. Okay, and so this is telling me that pi t has, so if you take a measure whose integral is bounded by the L1 norm for any function h, this is telling me that pi t, it's absolutely continuous with respect to the Lebesgue measure, and that its derivative is bounded by 1. It's absolutely bounded by 1. Okay, because, well, if h has integral equal to 0, this also has integral equal to 0, which is telling me that pi t, it's absolutely continuous with respect to Lebesgue. Okay? So it's absolutely continuous, and its derivative is bounded by 1. And with the same reasons, we can show that it's positive, because if I take h positive, this will be positive. So from this, I can conclude that for any fixed t, pi t, it's absolutely continuous with respect to Lebesgue, and its Radon-Nikodym derivative, its density, it's positive and bounded by 1. Okay? So with that, I conclude exactly this. And moreover, I know that rho tx, it's positive and bounded by 1. So, and this is for free. This is just the fact that there is at most one particle per site. We didn't use anything. So we get this for free. Yes?
The absolute continuous property, it also comes from the fact that there is most one particle effect? Or
Yes.
you could relax the condition?
I could relax the condition. Okay? I could relax the condition. Okay. For models in which you have you don't have a bound on the total number of particles per site, you still can prove that, but then you need to show that particles do not accumulate over a site. So you have to, then you need a dynamical argument to show that this does not happen. Okay. Here it's for free. If in other dynamics in which you, for instance, these random walks, there is no bound on the total number of particles per site, there you need an argument. A dynamic, you can still prove it, but you need to show it. So here, this is what we get. So we can, up to this point, we proved two properties of any limiting point, is that they satisfy, so they are concentrated on trajectories rho, which satisfy that, and also that pi, well, the measures are concentrated on absolutely continuous measure. So this means that I can rewrite, so this is the integral of g with respect to pi t, but since pi t it's absolutely continuous, this I can write that as gx, so now it's an integral over the torus, rho tx dx, and say that this is equal to t gx rho 0x plus 0 from 0 to t ds dx rho s x g double prime x. Okay? So this is what we obtained. So now I'll say that a function rho from 0t times the torus to 0, 1 is a weak solution of the heat equation dt rho. It's equal to the Laplacian of rho. Right? So this is what I'm saying. If you take integrated by part twice, formally, what you get is that you have this identity for all g. So this is telling you that the rho at time tx, it's equal to rho at time 0x, plus, if I change the order of the integrals, the integral from 0 to t of rho s x, the second derivative of rho s x. Okay, so maybe, okay, let me do this computation. Just so now, before I give you this definition, let me just remark that what we obtain can be written as formally. So I integrated the last term twice by parts, since we are using periodic boundary conditions. And what appears, if you change the order of the integration of the last term, okay, what you get is that for all g in C2, formally that this is equal to 0. Okay, I just rewrote this expression here. and where I integrated by part twice the last term. So this is what we get, but this is true for any g in C2, which means that this expression has to be equal to 0, almost surely, because if it's not equal to 0 almost surely, I can find a g for which this is not equal to 0. So I get that, from this, I get that rho tx minus rho 0x minus the integral from 0 to t second derivative in x of rho, that this is equal to 0 almost surely. And now if I take, well, this is equal to 0 almost surely, this means that rho t is differentiable almost everywhere, and that its time derivative, it's equal to the second derivative of rho. Okay? And from that I get that dt rho, it's equal to d2x of rho, which is the equation I wrote here. Okay? So I will say that a function rho from 0t, this is the torus, to 0, 1, it's the weak solution of this equation with initial condition rho 0 if for all t and for all g I have that this equation is satisfied. Okay? And so this is very nice because it doesn't require any regularity on rho. Rho, it's just a bounded function defined on 0t times the torus. So I can make sense of this equation by taking smooth test functions and integrating by parts to remove all derivatives from rho to the test function. So I'll say that rho, it's a weak solution if it satisfies that equation. And what we did is that we proved that any limiting point, it's concentrated on weak solutions of the heat equation with initial condition, which is given by the initial condition where we started from. Okay? Remember that this rho, it's exactly the one which appears here. And now we need a theorem telling us that there is a unique weak solution of this equation. Okay? So you have to look at in the literature and find a theorem which tells you that there exists a unique at most one solution. So that for any rho 0, there is at most one solution of this equation. Okay? And there are plenty of theorems in this case, which is very simple because the equation is linear and you have a Laplacian. And this proves uniqueness, okay? Because you proved first that all limit points are concentrated on weak solutions, and then you found a theorem which tells you that there is only one weak solution. So you proved that this limiting measure, it's concentrated on one deterministic trajectory, which is the weak solution of this heat equation. And this completes the proof of uniqueness. And this is the way in which you will prove uniqueness, okay, for these interacting particle systems. You'll show that they are concentrated on weak solutions of certain PDEs. And then you look at these theorems of uniqueness. And maybe the theorem of uniqueness requires some smoothness of your trajectory. Maybe you need to show that, well, there is a derivative in L2. So there is a weak derivative. Then you have to prove that these regularities are fulfilled in order to show that the empirical measure is converging to the weak solution. But this is this will be the strategy. Right? You'll write the martingale. You'll show that the martingale converges to 0. And the martingale will tell you what is the PDE. Okay, here it was extremely simple, because when we computed the martingale, this term here, it's a function of the empirical measure. So the equation, it's closed in terms of the empirical measure. In other words, the martingale could be expressed in terms of the empirical measure. In general, this is not the case. And then you'll need an argument to close the equation. So when you write down, you compute this term will be not, in principle, a function of the empirical measure. It will be something complicated. So we'll see in the next example. Okay? Then you'll understand my observation here. But what I'm saying is that this model is extremely simple, because when I computed the martingale, what I obtained, it's a function of the empirical measure. And that, it's a very special property of the symmetric exclusion process. And we'll see tomorrow, or maybe the day after, that in other models this is not the case, and then we need an extra argument to close the equation, to express the martingale as a function of the empirical measure. So questions about uniqueness? But this is the strategy. Yes?
There is this kind of theorem that tells us if the generator has some character, then the martingale can always be written in terms of empirical measure, or such theorem doesn't mean.
Well, it exists one which tells you that the unique case, it's the symmetric exclusion process. No, it's not a theorem, but it's a miracle that it is so. That you'll see, whatever interaction you put between particles, then you get something different. Something which is not a function of the empirical measure. There are two cases, symmetric exclusion process and independent particles. Everything else will not be a function of the empirical measure. Well, we'll see. Any other question? I mean, this is a very special property. And, well, and it's related to linear equations, so. Okay, so this is, as I said, if you want to prove that this sequence converges to a measure, you proceed in 2 steps. You first prove uniqueness, and then you prove tightness. So we proved uniqueness, so now let's consider tightness. And tightness, I told you about tightness in these spaces, and I proposed the Ahlus criterion. So the Ahlus criterion was, you take a stopping time tau, which is bounded, say, by t, and what you have to estimate, it's the distance between your process, so this is in the space of trajectories, of tau and tau plus a. And you have to show that this is, that if you take the limit sup in n, and then the supremum over all stopping times t, the supremum over all a less than epsilon, and then you take the limit as n tends to infinity, that this has to be equal to 0. And then epsilon to 0. So epsilon is the size of a. So you look at tau and tau plus a, but a is bounded by epsilon. So you take a supremum in t, you send n to infinity, and then epsilon to 0. And this has to be equal to 0 for all delta. Okay? Fine. So what is the distance between two measures? We have seen that the distance can be written as this 1 over 2k, and then, let's say, pi tau fk minus pi tau plus a fk. And this is divided by 1 plus the same difference. So it's clear that from this definition of the distance, that if you want to show this, it's enough to show that this difference satisfies this inequality. Okay? Because, well, you choose a case sufficiently large for this to be bounded by delta over 2, and then you have to consider only this finite number of cases. So actually, for this topology, in order to prove tightness, what you need to prove is that for all f, you can take it as smooth as you wish, let's say C2. For all f, you have to estimate the distance between pi n tau plus a f minus pi n tau f. Okay? You have to show the same thing, but for smooth functions f. So you'll take the supremum over stopping times bounded by t, supremum over a bounded by epsilon, and then you take first a limit in n and then in epsilon. And here again, I will use the martingales. So remember my definition of the martingale Fn. So this will be written as my martingale at time tau plus a minus the martingale at time tau plus the integral from tau plus a. The expression which appears here, which we have seen, it's pi n s g second, or Laplacian, discrete Laplacian of g. Or now it's f. Okay, so if you remember that mn was at time t was this expression at time t minus this expression at time 0 minus this expression at time from the integral from 0 to t. Should I? Okay, so this at time t was pi n. Mind that my time is speeded by n square. Okay, so this is the definition of my martingale. So now if I consider my martingale at time tau plus a minus the martingale at time t, what you'll get here is this difference, and then an integral from tau to tau plus a. Okay? Maybe there is a wrong sign. But I don't think. I think the signs are correct. Okay, so I'm able to express this difference in terms of my martingale and an integral. And why this is nice? Well, this is nice because this expression here, since f it's in C2, Laplacian of f it's bounded. It's a continuous function. The second derivative is continuous, so it's bounded. Pi n, there is at most a particle per side, so this is bounded by a constant, and this integral is from tau to tau plus a. So all this expression, it's bounded because a it's bounded by epsilon, it's bounded by a constant times epsilon. Okay, so this expression is bounded by a constant epsilon. And since I'm saying delta is fixed and epsilon is converging to 0, I don't need to bother with this integral, this piece. Okay? So actually, in order to estimate this, I just need to estimate this expression. Okay? So it's enough to prove well, it's enough to estimate so I can use Chebyshev to say that this is bounded by 1 over delta squared, the expectation of the square. But now, since m it's a martingale, as a function of a, this is a new martingale, and this square, by the formula we obtained, so let me do one further step. So let me compute this square. So what I get is that this is m fn at tau plus a plus m fn at tau square, and then minus 2 m fn at time tau plus a times m fn at time tau. And this is the expectation of this expression. So let me consider the last term. Let me take the conditional expectation, say that the expectation is equal to the expectation of the conditional expectation, and let me take the conditional expectation with respect to the sigma algebra associated to the stopping time tau. When I do that, this expression is measurable with respect to f tau, while this one, well, this is a martingale, and so the martingale satisfy the identity even for stopping times. So remember what was the definition of the martingale was the expectation at time t given fs, it's equal to ms. So the same thing can be extended to stopping times. So the expectation of this martingale at the stopping time tau plus a, given ft tau, it's equal to m at time tau. So this one gets out and this one becomes m tau. So what I get is that this becomes minus 2 m tau square. Here I have plus m tau square, so I get a minus here. Okay? So this computation tells me that this square is actually equal to that one minus this one. So the expectation of this square is actually equal to the expectation of this one minus the expectation of that one. And now I recall that the expectation of m at time t square, that this is equal to the expectation from 0 to t of gamma s ds. Well, and the same thing, because why? Because this expression minus this one, it's a martingale. So the same thing holds if I replace these times by stopping times. Okay, because this is still a martingale. Okay. The martingale, what we know about martingales is that if fx nt it's a martingale, then this is constant in time. But we can extend, so this is equal to n0 for all time t. But we can extend this identity to stopping times which are bounded, to bounded stopping times. And this is exactly what I'm doing here. I know that this expression minus this one, it's a martingale. So it's constant, but this martingale is 0 times 0. So its expectation is constant equal to 0, which means that the expectation of this expression is equal to that one at any time t. But now I'm replacing times by stopping times because I have this result. Okay, so I know that. And therefore, this expectation, which is the difference at time tau plus a and at time tau, that this is simply, so this expectation, it's equal to 1 over delta square, the expectation from tau to time tau plus a of the gamma n s ds. Okay, but gamma n, we proved it's bounded by 1 over n, by a constant divided by n. So this expression, it's bounded by a constant times a divided by n. So this one is small. And that proves tightness. That proves that Aldous' criterion holds. Therefore, we have tightness, we have uniqueness of limit points, and that shows that the sequence converge. So we proved that for the symmetric exclusion process, we have the empirical measure, the distribution of the empirical measure, converge to the unique weak solution of the heat equation. Okay. Just an observation, we didn't use that the initial measure was a product measure. We just needed the convergence at time 0. So we needed that this expression was converging. Okay. So we can start from any measure for which these integrals converge. And then you don't need the initial state to be a product measure of Bernoulli's. associated to a density profile, you can take any initial measure for which this is converging to, well, I erased, but to the integral of rho 0 with respect to f. What you mean that, well, I just proved that this limit, well, okay, I have two pieces, right? There is one which converge only when I send epsilon to 0. And the other one which is very small. This one converges to 0 when I send n to infinity. But I don't think I proved more than tightness because, well, there is still this piece, the integral piece, which is which converge only when I send epsilon to 0. Okay, so this is how we will prove the hydrodynamical limit. We will write the martingales. The proof of the tightness will be exactly the same. Okay. That won't change much. But the proof of uniqueness, that, as I said, relies strongly, well, we here use strongly the form of the martingale, and you'll see in the next example, maybe I still have time, I can introduce that today so that you just start thinking about this model. You'll see that now the martingale will not be easily expressed in terms of the empirical measure. So let me introduce the model which I would like to consider next. So the model, here what we did, we defined the exclusion process as exchanging two neighbors with rate 1. Now the rate at which you exchange neighbors will not be 1, but will depend on what happens in the next neighbors. So the model which I would like to consider now, it's still, okay, I don't see, here's it. So I still work in lambda n, which is 0, 1 over n, so the discretized version of the one-dimensional torus. And I still allow at most one particle per site, so the state space will be 0, 1. Configuration will be represented by eta. And again, the rate at which I jump from eta to psi will be different from 0 only if there exists an x such that psi is equal to sigma x plus e of eta. So the only thing I'm allowing is to exchange eta x and eta x plus e. But the rate at which this happens, for the exclusion it was 1. Okay? Now it's not 1 anymore, but it's 1 plus a, which is eta x minus e plus eta x plus 2e. Okay, so there is the site x and x plus e. Okay? So I look at what happens at x minus e and x plus e, 2e. So here is the site x, x plus e. So I look at what happens here and here. Okay? If these two sites are empty, then the rate is 1. I exchange x, eta x and eta x plus e at rate 1. But if there is one site it's empty and the other site it's occupied, then I will jump at rate 1 plus a. And if both sides are occupied, then I will jump with rate 1 plus 2a. Okay? So the rate at which I exchange now depends on the next neighbors. I want this to be positive. So this means that 1 plus 2a has to be positive, which means that a has to be larger than minus 1/2. But a can be negative. Okay? A can be negative, but has to be larger than minus 1/2 because I want this jump rate to be positive. Okay? And then it's 0 otherwise. So the only jumps are still the same, I exchange, but now the rate at which I exchange depends on what happens at the nearest neighbors. Okay. And so here's the dynamics, and I want to prove the hydrodynamical limit of this process. So the strategy will, as I said, be exactly the same. My first observation is that the Bernoulli measures are still invariant. So I claim, so as I said, as soon as you introduce a new dynamics, the first question is, let's see what are the stationary states. And I claim that here the stationary states are the Bernoulli measures, or the uniform measures, if you wish. And these are reversible. Okay? And to show that they are reversible, it's enough. So you see that, let's say, that I want to prove that the Bernoulli measure it's invariant. What I need to show is that it's reversible. I need to show that this holds, okay? But if psi, so there are two possibilities. Either there exists x for which psi it's equal to sigma x plus e of eta, or there are not such x. If there are not such x, this means that these rates it's equal to 0. And it means also that these rates it's equal to 0 because if psi is different from sigma x plus e eta for all x, it's also true that eta is different from sigma x plus e for all x. So these two, in these two cases, in this case, both rates are 0, and this identity is satisfied trivially. Now, if psi is equal to sigma x plus e, then this measure is equal to that measure. You just exchange, so you can check that nu alpha eta is equal to nu alpha psi. And what you need to prove is that these two rates are equal, so that the rate is symmetric, but the rate is clearly symmetric because the rates do not depend on x, eta x, and eta x plus e. So you exchange, or if you keep it, since the rate do not depend on eta x plus e, this is symmetric. So I went fast. Please check carefully that indeed these two measures are reversible, so that they satisfy the detailed balance condition. So the invariant states are exactly the same as the exclusion. Now let's compute the martingale. So you fix a function g, which is C2, And I want to compute the martingale, which is pi n tg minus pi n 0g minus the integral from 0 to t of L and pi n s g ds. Okay? So I have to compute this term. So let's compute that. So I'm computing this expression. And as I said, this is the sum for x in lambda n. Okay. So once you have this rate, you can find, so maybe I'm going too fast, so let me compute what is the generator. The generator applied to a function f computed at configuration eta is, by definition, the sum over all xi, or n eta xi, times f of xi minus f of eta. Right? But these rates are all 0 unless there is an x. So all terms here are 0, but those for which xi is equal to sigma xx plus e eta. So this is actually a sum over all x, in which I take xi to be equal to sigma x, x plus e of eta, okay, so this is the generator, and now I will replace R by this factor. So this is the generator, and now I'm applying the generator to pi g. So I just write here the generator, which is 1 plus a times eta x minus e plus eta x plus 2e. And then this is f after the exchange. So this means that I'm computing pi at sigma xx plus e eta g minus pi g. So that did not change. So now I just want to compute this difference. So this difference, it's 1 over n. I'm summing over all y. And here I'm taking g of y times this configuration, sigma x, x plus e at eta, computed at y. And this minus 1 over n, y, g of y, eta of y. Okay, so this is what we need to compute. And you see that these two terms are equal for all y, but y equal to x and x plus e. Because this consists in exchanging what happens at x and x plus e. So if I compute at y, it's the same. So this sum, it's equal so this sum, we did that already. It's equal to 0 for all y, but y equal to x. So let's see what we get at y equal to x. At y equal to x, so this is gx. here, this is x, but we are exchanging x and x plus e. So this is eta computed at x plus e. And here is y equal to x, so we get minus eta x. And then we have a second term when y is equal to x plus e. When y is equal to x plus e, so y is x plus e, x plus e, therefore here it's x, and there it's x plus e. And so now let me write what we obtained. We have this 1 over n. Here I can rewrite this sum putting x plus e minus eta x, so I get a minus sign here. So this is minus 1 over n gx plus e minus gx times eta x plus e minus eta x. Okay, so this is, I have a minus sign. Let me write what we have over there. It's 1 plus a times eta x minus e plus eta x plus 2e. Then here, eta x plus e minus eta x, and gx plus e minus gx. Okay, and now you see that you can, what happened for the exclusion? The exclusion, we did not have this term. Okay? This was simply 1. So for the exclusion, we could integrate it by parts again to get eta x times the Laplacian. But here, it seems not possible to integrate by parts because we have this expression. But I chose it carefully to be able to integrate it by parts. You'll see it. And it's because we are able to perform, here you see I have a difference of g. By integrating by parts, we'll get a Laplacian. So this is a term of order 1 over n. By integrating second time, it will be a term of order 1 over n squared. And that will simplify a lot. If I could not perform this second integration by parts, I would be in trouble. So the models for which I can integrate it by parts a second time are called the gradient models. And I'll show you that here I'm able to integrate it by parts a second time. Okay? By looking at this function. In the one, I can integrate by parts a second time, right? If I multiply this difference by 1, then it's easy, I did it already. I can sum by parts this expression. Now let's see how I sum by parts this expression. And this is why I was very careful by choosing this rate. So you see, I have there a times eta x minus e eta x plus 2e times eta x plus e minus eta x. So this is a. Now I have eta x minus e, let's say eta x plus e. So these are these two terms. And I will compare these two terms with these ones. So this is minus eta x plus 2e. And then, so I took this and this. Now I have to take these two. So plus eta x plus e, eta x plus 2e. And then I took these ones. Now I'll take these ones minus eta x minus e, eta x. Okay, and what we see is that we have here a function, x minus e, x plus e, and here this function translated by 1. Here I have this function, and here it's the same function, but translated by minus 2. So I'm able to write this product as functions minus the translated. And since I'm able to write this function minus its translation, I will be able to integrate by parts, to sum by parts, a second time, to get the Laplacian of g. So now imagine that I did not have this term. I would simply write the rate as 1 plus a times eta x minus e. In this case, what would appear here, it's a times eta x minus e times eta x plus e minus eta x. Okay? And I'm not able anymore to write this product as a difference of a function minus a translation. There's nothing I can do here in order to write this product as a function minus its translation. And therefore, if I had defined the rate without this term, I would be in a serious trouble, because I would not be able here to sum by parts. So the models, we have the exclusion. Then we have the models at which I can sum by parts. These are called the gradient models. And then there is a class of models, which are the general models, which are called non-gradient. And these ones are the ones for which I cannot integrate by parts. I cannot sum by parts a second time. Okay. So there is a theory developed by Varden to prove the hydrodynamical limit of non-gradient, which is quite complicated. So I will not present it. I will concentrate on the gradient models. Okay? But, okay, there is still research going on non-gradient and gradient models. So, but I hope that at least you understand what is the problem. Okay? What is the difference? So here is a big difference between these two models. So now here I'm happy because I can sum by parts. So I still have time, so let's go and sum by parts to see what we get. Because we are not done yet. I mean, though these models are much simpler than the non-gradient models, there's a lot to do yet, still. So I have first the 1. So let's go back to this, okay, to this expression. So I have here the minus this difference, and that will give me eta x. So with plus eta x, I get gx plus e minus gx. And then I have here the minus eta x plus e. So I change that into x. So here I get x and x minus e. And I have a minus sign, so I get plus gx minus e. minus gx. Okay, and this is exactly what we obtained for the symmetric exclusion process, because everything here is now, I still have 1 over n. I'm very happy because here I have the empirical measure computed at the discrete Laplacian of g. Okay, so this is the first term. Now I have the terms in A. So let me write them here, plus a's over n. And this is this product. So I have minus so let's say that I have this is line 2, and this is line 3. So let me compute line 2. So this is the sum for gx minus gx plus e, which is that expression with the minus sign, gx minus gx plus e. And there I have eta x minus e, eta x plus e, minus eta x plus e. So so this is line 2. And I will keep this function. So I want to change variables for that one. So this is a over n. So the function will be eta x plus e. Plus 2e, sorry. Okay. So for this one, I get, there is a minus sign, so gx plus e minus gx. And now I have this term, so I want this term to be x plus 2e, and this term x. So I'm translating, I'm calling x minus e x and x plus e. And I have a plus sign, so this is, so x will become x plus e. And x plus e will become x plus 2e. Okay, so this is, if I did not any mistake in my computation, this is the second line. And then I have the third line. Maybe I can compute the second line up to the end. What I want to do is a Taylor expansion of this term. Okay? So let me expand in Taylor this expression. So the first one, I'll get g of x plus 1 over n g prime of x plus 1 over 2n square g second of x. Okay, so this is the expansion of this term. Oh, on the first one. So gx, I leave it as minus gx. Then gx plus e, it's the same as the first one, so I just get a 2, and a 2. And then minus gx plus 2e, so this is gx plus 2 over n gx prime plus 4 n2 1/2 gx second. Okay, so these are the Taylor expansion over all these terms. So you see 2 of gx cancel with minus and minus. And then the first order term I have here plus 2g prime, and here I have minus 2g prime, so they also cancel. And what I get, it's only the second order terms survive, and I have 1 over n square, and so with a plus and minus 2, so I get minus 1 over n square g second prime plus smaller order terms, right? So what I get is that this is equal to line 2. It's equal to a over n. Then I have minus 1 over n squared sum in x of gx double prime times eta x plus 2e. Okay, so this is line 2. And here's the difference, because while here I had eta x, so this was a function of the empirical measure, now I have the second derivative of g, but multiplying by eta x and eta x plus 2e. And this is not a function of the empirical measure. So we are in trouble. This is what I was saying. For the exclusion, you compute and you're very happy because what you get, it's a function of the empirical measure. It's just the empirical measure which is integrating the second derivative of g. But in this model, though I'm able to perform this second summation by parts, what I get, it's not a function of the empirical measure. Okay, so this is line 2. Let me compute line 3. So again, line 3 will be gx 1 over n, a, sum in x, gx minus gx plus e, and then I have these two terms, this difference, eta x plus e, eta x plus 2e, minus eta x minus e eta x. Okay, so let's say that I keep this one. So that will be minus, plus a over n. So I just repeat the same computation, eta x minus e eta x. But there is a minus sign, so that's gx plus e minus gx. And I want to change these into that. So x plus e, x plus 2e is x prime. And so this means that x, it's x minus e, minus 2e, and x plus e, it's x minus e. Okay? Correct me if I'm... If there is a mistake in my computations. And now again, I will do an expansion, Taylor expansion of these terms. So let's took the first one, which is g plus at x plus e. So this is equal to gx plus 1 over n g prime x plus 1 over 2n square gx double prime minus gx, then plus gx minus 2 over n gx prime minus 4 n square 1/2 g second, and minus gx minus 1 over n gx prime plus, oh, is this a minus or is this a plus? Plus 1 over n square 1/2 g second. Okay, so let's see what we get from that. So here's gx minus plus minus. That's fine. Now there's a plus 1, minus 2, plus 1. So looks good. First derivatives are going away. And for the second derivatives, then I get 1 over 2. Here I get plus 4. And then here minus 1. So I get plus 2. If I did not any mistake. So finally, so this means that third line, it's equal to a over n eta x minus e eta x times 2 n squared and g second. Okay, so this is the martingale. It's the sum of this term in which I have the Laplacian. I'm very happy, but there are two terms. The second term, line 2, and line 3, in which I get something which is not a function of the empirical measure. And the problem for these models, the gradient models, it's to replace this function by a function of the empirical measure. It's to close the equation so that you can pass to the limit. Okay? Because if you express everything in terms of the empirical measure, then you can go to the space D and pass to the limit and check for the limiting points, properties of the limiting points. But here we cannot pass to the limit because, well, the martingale, it's not a function of the empirical measure. Okay? So this is our goal. It's how to close the equation. And that will require some time. So some ideas and some techniques which were developed by in the end of the 80s, which I will present in the next class. So questions? Okay, so we stop here and we continue tomorrow.